Hi everyone, my name is Daniel. Today I'm going to be discussing Lab 1 Constant Velocity of Physics 2211. Let's get into it. I'm going to start with our table of contents. We're going to begin with our overview of the lab, move on to Newton's second law and its relevance to the lab. I will then move on to tracker discussion and discuss the software. I'm going to then continue with a discussion of average versus initial velocity and how I found the two. I will continue to discuss computational models and the one I made in GlowScript, then a presentation and comparison of the data through graphical analysis. I will then present a summary of the net forces, potential causes of error, and then end with a wrap-up of the lab. The purpose of this lab was to test out Newton's second law and see it in action. In this lab, observation of an object's velocity and change in position while it is moving at constant speed in one direction was done. First, we tracked the experimental movement of an object through the computer program Tracker. Then, I constructed a computational model through the GlowScript integrated development environment by applying the principles of Newton's second law. I then compared the experimentally measured position data with the computational model which I created in GlowScript, predicted position data. In order to understand the purpose of our lab, it is important to understand Newton's second law. Newton's second law relates acceleration with net force and mass, specifically saying that the acceleration of an object is directly related to the net force and inversely related to its mass. In the context of this lab, we can derive the following formula. We assume that the net sum of the pushes and pulls, or Fnet, are zero, which then brings us to the following formula. Velocity final equals velocity initial. This equation, simplified, leads us to a position relationship, where the final position is equivalent to the initial position plus the average velocity times the change in time. We then apply these principles in our computational model. Before I show my video in Tracker, it's important to understand these initial assumptions and data. The diameter of the cardboard cylinder that I'm rolling is 7.62 centimeters. The total distance that it travels is 75.962 centimeters. The choice of axes is the plus x direction to the left and the plus y direction up. If the positive x direction was selected in the opposite direction, it would simply make the displacement data in the negative direction. Moving on to a demonstration of our Tracker software. In this video, you see the cardboard cylinder rolling across the floor at a constant velocity. The plus x-axis is to the left, and on the right of your screen, you should be able to see a graphical data view as well as a table of time against displacement. It is important to understand which velocity of the rolling cylinder we use to understand how we apply the computational model. There are two choices for which velocity to use in our computational model. First of all, we can use the measured initial velocity in our computational model, which would lead to a large error when comparing the changes in position. This is due to personal human error. The initial velocity of the cardboard cylinder is not actually constant throughout. There's a slight stronger push at the very beginning, which leads to a velocity that slows down slightly. It's not equivalent to the velocity throughout, which leads to a poor prediction. Using the measured average velocity in our computational model leads to a negligible error as compared to the measured initial velocity when comparing the changes in position. This is because using the average velocity is a much better indicator of what the velocity is throughout the path of the cylinder, which leads to a much stronger prediction of change in position. To find the velocities that I then used in my computational model, I conducted the following calculations. By definition, the change of velocity, delta v, is v final minus v initial divided by change in time. Initial velocity computation was the following: 2.737 centimeters minus 0.398 centimeters divided by the change in time, which is 0.7 centimeters per second. The average velocity was 76.36 centimeters minus 0.398 centimeters over the change in seconds, which led to 0.8584 centimeters per second. Continuing on to the computational model and the code that I wrote for it in GlowScript, we can view now on lines 58 and 60 in the given screenshot how I applied Newton's second law and where I apply the velocity of the moving object. On line 54, it is also visible that I assume that Fnet is 0, for reasons that are discussed later. I will now compare the collected experimental results with the expected results created by my computational model. On this first slide, you can see a graph demonstrating the measured data created through our experiment against the predicted data created by GlowScript computational model using the initial velocity in the programming. Here you can see a very clear discrepancy on the graph between the measured position and the predicted position over time, while the two data trends do begin quite close together. As time continues, the two predictions of position and the measured position go farther and farther apart. This is a result of the initial velocity being used in my computational model. Because the initial velocity is not a perfect measure of how my object, which is this cardboard cylinder, is going to move throughout the whole thing, it's not actually that good of a model. It's clear through this graph that a computational model that utilizes not the initial velocity, but the average velocity, which is obtained through using the initial position and the very final position, is a much more exact model than using the initial velocity as my computational model. Here you can see very little discrepancies through the position over time. The graphs are almost identical. This shows us that using the average velocity is a much better model. This experiment does have many potential causes of why observed/experimental data does not align with the theoretical computational model used. For example, human error in the initial experiment. I used too strong of an initial push, which led to an initial velocity that then slightly decreased, instead of a velocity that maintained perfectly constant. Also, tracker selection and accuracy. Self-selection of the center of mass of the object is not necessarily precise due to human error. Just because of the nature of this program, there is a potential for error. Also, why can we assume F net equals 0? Because there are four forces acting on the object. The force of the ground, which is the same magnitude as the force, which is the weight of the ball or the other object into the ground. There's also the force of the friction and the force of the initial push. These four forces balance out and allow us to assume that F net equals 0. Thank you. This concludes my lab presentation.